So we are discussing about the measurement of slip in induction motor. See, slip, as you know, is given by the ns minus nr by ns, where all these speeds are mechanical speeds. Ns is the synchronous speed, ns is synchronous speed, and it is given by 2f by p, and nr is the rotor speed. All are mechanical speed, rotor speed. Okay, so this is slip. So the measurement of slip accurately is necessary because the production of torque in an induction motor in this stable zone depends on the accurate measurement of slip. Is not. If you remember the torque slip characteristics of an induction motor, it is somewhat like this. And the stable zone is confined only in this linear portion of the induction motor and which spans over a very little value of slip. So here if you make slight mistake in the estimation of slip at which induction motor is running, you will be making greater mistakes in your calculations. So accurate measurement of slip is necessary to predict the performance of the induction motor. Now what is to be done? So one way of doing it, as I was telling, use tachometer simply. Suppose you know it is a 4-pole machine, 4-pole induction motor, and supply frequency is f or 50 Hertz if it is. Then synchronous speed can be calculated, which is 1500 RPM, and then measure the rotor speed with the help of a tachometer. That is the easiest way of doing. But as you know, tachometer often gives wrong results and very difficult to distinguish between the least count of the tachometer also counts. Therefore, because of this, some accurate measurement of slip is necessary. So one way of doing this in case of slip ring induction motor is also, I discussed last time. What is that? In the rotor of the induction motor, you connect a zero-centered DC ammeter, and count how many oscillations it makes. So that will be the frequency of the rotor current. And frequency of the rotor current, as we know, is related with slip by this relationship. So just by physically counting the number of oscillations the ammeter pointer makes, you can get the value of FR and supply frequency is known. Therefore S can be calculated. However, in case of cage induction motor, you cannot do that because in the rotor nothing is available, no terminals, etc. are available. And also the ammeter connection, if the machine operates at larger value of slip, the oscillations will be quite fast. See, 2 Hertz, 3 Hertz, it is okay, you can read it. But if the slip becomes too large, then difficult to read. Because of these things, another method, a very well established technique, that is called stroboscopic method, that I just started last time. Stroboscopic method for slip measurement, This method I was discussing. The essence of the thing is very simple. In the stroboscopic method, what is attempted is to determine, instead of in absolute value determining the value of nr, what is done, this difference is measured. This difference is measured or obtained. Instead of you calculate in absolute terms what is the rotor speed, you try to calculate the difference of this speed. This is also known as slip speed. So this slip speed you try to calculate by the stroboscopic method. You see, the slip at which machine will be operating is quite low. Therefore, this ns minus nr will be quite low. Although nr may be quite high, ns may be quite high, but the difference will be quite low. Now the essence of this measurement lies in this fact that suppose a rotor, anything, any moving object or rotating thing, suppose it rotates very slowly. Suppose a moving thing rotates at a very low RPM. then that RPM can be measured just by physically looking at it. What I am trying to tell, suppose you have a circular disc and you mark with your chalk something here on the rotor body. Now suppose it rotates at a very low RPM. Then I can just by counting this point in a given time, I can accurately tell what is the RPM. Is not? Suppose it is running very slowly. Suppose 1 RPM, 2 RPM, 10 RPM it is moving. Therefore, just by putting a mark on the rotor, and I can count how many rotations it makes in a given time, and from this I can calculate its RPM. Of course, this method will fail if it runs at a very high speed. Suppose your DC motor or induction motor is running at 1450 RPM. You put a mark initially. You cannot really make out where this mark has gone when it runs at a very high speed. However, if it runs at a very slow RPM, then by putting a mark it will certainly help me and help me to correctly assess the speed of rotation of that rotor. But the point is here, rotor will run at a very high speed depending upon the synchronous speed of the motor, just below that. Therefore, however, this is the essence of the thing, how it is obtained. Now, a stroboscope is a device. It essentially consists of a neon lamp, a box-like thing. It looks like a neon lamp. It has ultimately at its output, and this circuit, this neon lamp, is made on and off by some electronic control circuit inside. Now, a line frequency stroboscope, line frequency strobo. I will tell you what it is. Line frequency strobo. In short, they are called strobo. What is the line frequency strobo? That is, this stroboscope is given that input supply voltage from the line, existing main supply voltage. The flashes it gives out, that is, it will give out in a cycle, 50 cycles suppose is the supply, then it will give out 100 pulses of light. Okay, suppose that is, it will go on and off 100 times in a second. Okay, that flash, it is some charging discharging circuit will be there, RC circuit. Let us not go into detail. What I am trying to tell, this line frequency strobo will have a neon light connected, and it will give light not continuously like this lamp. Okay, it gives you flashes of light. How many flashes it will give? It will give twice F number of flashes in a second. If F is the supply frequency, number of flashes given out will be twice F. That is 100 times it will give light in a 50 Hz system. If the supply frequency is 40 Hz, it will give 80 pulses of light per second. Like that, that thing works. It is called a line frequency strobo. Now, how this can be utilized? Let us see in measurement of sleep. What you do, suppose on the rotor of the induction motor, and let us take a very fixed example. Suppose it is a 4-pole machine. 4-pole induction motor. Suppose the supply frequency is 50 Hz. What you do, you make some 4 marking on the rotor. Equi-spaced 4 markings on the rotor you make. Identical markings. And don't name them, but for understanding I will name them. Suppose let us call this marking is named 1, 2, 3, 4. These 1, 2, 3, 4 are not written on this marking. They are just marked on the rotor. Okay. And suppose it is a 4-pole machine. Now what you do, you bring this stroboscope in front of this disc. So it will flash light on the disc. Okay. Light pulses will be on the rotor. Let us assume, suppose the machine is running absolutely on no load, that is NR equal to NS. Synchronous speed of the machine is equal to NR. And suppose this is T equal to 0 when first flash of light falls on this rotor. Okay. What is the time interval between two consecutive pulses? It is 1 by 2f second, is not? So time interval between two consecutive pulses of light, two consecutive light flashes will be equal to 1 by 2f second, because in 1 second it gives 2f pulses, so 2 consecutive. So let us see what happens at t equal to 1 by 2f second. And let us assume rotor speed is equal to ns. Then once again you draw the rotor. Suppose nr equal to ns. And you remember ns equal to 2f by p. Therefore, this pattern, this marking will also move by that time. By what distance the pattern, say one pattern will move? By what RPM? See, in what is called 1 second, rotor moves by NR, that is equal to NS in this case. So much RPS. So in 1 by 2f second, it will move NS by 2f. So much RPM it will move in this 1 by 2f second. And when NR equal to NS, that case I have taken first. Rotor speed is equal to synchronous speed. Then for that reason NR equal to NS I have put. And this will then become equal to how much? 1 by P only. That is, rotor will move by 1/5 of the pole pitch. So in this case, P is equal to 4. So it will move by a distance of 1/4, quarter. 1/4 of the circumference it will move. That is, after this one, at t equal to 1 by 2f, your patterns, this one will come here. 2 will come there. 1/4 distance each one of them will move. And it will come here, it will come there. So this will be 3, 4. Okay. Once again, after 1 by 2f second, another pulse comes. Okay. At that time also, this whole pattern will be shifted by another 90 degrees. This one will come there, like that. So ultimately what you will see? You will see the pattern to remain stationary. Because 1, 2, 3, 4 I have not written. I have only marked them. For my understanding purposes, I have written 1, 2, 3, 4 here. So this pattern will appear to be stationary. There is no movement. In fact, rotor will appear to be stationary. So in a somewhat darker environment, if you flash the rotor, which is marked with these 4 patterns with this stroboscope, rotor will appear to remain stationary. Although rotor physically is moving at a speed nr equal to ns. But anyway, in this case, therefore, slip is 0 in this particular case. Now let us see what happens when the rotor moves at a speed less than ns. That is what will happen in case of an induction motor. So once again, suppose you assume this is the rotor. This is suppose the rotor. This is suppose 4 markings you do before you start the machine on this disc. which is attached to the shaft of the machine. And I am just naming them 1, 2, 3, 4 like this. And this is suppose t equal to 0 situation. Now the speed of rotor is less than ns. And ns is 2f by p. And p I have assumed in this case, of course, 4-pole machine. If it is a 6-pole machine, I would have marked with 6 markings. If it is 8-pole machine, 8 markings, like that. So as a special case, suppose p equal to 4. Then this is the situation at t equal to 0 when the first flash comes on this shaft and the pattern is here. Okay, at this point. Second pulse will come at t equal to 1 by 2f second later. So at that time, how this pattern will look like, I want to draw here. So for that, what I will do, for a given pattern, say the pattern 1 was here, so it will move, and the rotor rotates suppose in the clockwise direction. So how much it will move, by what RPM it will move, that point. So rotor speed is nr. Suppose let us assume this nr, ns, all this speed I am telling in terms of RPS, so that calculation becomes easier. Otherwise I have to live with that 60 if I express in RPM. It does not matter, no, ns minus nr by ns. You express either all of them in RPM or RPS, it does not matter. So suppose these speeds I express in terms of RPS. So in 1 second, this pointer moves by nr rotation rotor makes. So in 1 by 2f second, it will move by this distance. Not, this one will come here. If rotor, so this nr being less than ns, this one will not come at 2 now. After at t equal to 1 by 2, it was initial position. These points were initial position. This one, do you think it will come here now? If it were nr equal to ns, then it would have come here. So it will come somewhere slightly, it will fall short of this one, because nr is less than ns. So suppose one will perhaps come there, and then these other things, this will here will be this will be 1 finally. At that time, this will be suppose 2, this will be 3, and this will be your 4. This way it will come. Okay. Once again, next pulse comes. Then this one will fall short of 2 like that. In this way it will go. So physically what you will see? Physically, in compared to this one, where the rotor pattern appeared to be stationary in space, how it will see now? It will change its position. But which way and how it will look like? That is, suppose I have kept my eyes here. I have kept my eyes here. What I will see is that the pattern is moving in the opposite direction of rotation in this direction, in the anti-clockwise direction. Because this 1, 2, 3, 4 I have not written. Only the markings are there. So I saw a marking here. After some time, 1 by 2f second, I will see the marking there. And after another 1, 2 by f, this marking, I am not this physically, this marking will come, because it was 1, it has come 4. But it does not matter. The patterns are identical. So I will only see this pattern will move another by same amount in this direction. So the pattern will appear to rotate in the anti-clockwise direction if the rotor moves in the clockwise direction. And so what is the RPM of that motion? That will appear to my eye, I want to calculate. So how much do you think? This will be, see, this distance is, if it would have moved completely ns by 2f, this RPM, if it would have moved at ns ns rps, then ns by 2f, and it has moved now nr by 2r. So this and this are same by the same. So it will be simply ns by 2f minus nr by 2f. By this amount, as if this pattern has moved there. And this it has done in 1 by 2f second. So the pattern will appear to move in the anti-clockwise direction in such a way that in 1 by 2f second the pattern moves towards left in this particular case with this much speed. So per second what it will be? It will be ns minus nr straight. Therefore, see, ns minus nr is quite small. Ns minus nr is quite small. So what I will do? I will take a stopwatch. I will keep my eye fixed at a particular position on this rotor. The moment I see a pattern in this, I could keep my eyes here, there, everywhere. I mean, somewhere I will fix my eyes. Suppose here I fix. I will switch on my stopwatch when some pattern comes here. Switch it on. Okay. Then I will calculate how many these points passes in a given time. And I will try to find out what is the speed of rotation. As simple as that. So ns minus nr can be very easily calculated. And it is this ns minus nr calculation where we make mistake if I use a tachometer. That point I want to stress upon. That is slip measurement ns minus nr by ns. This ns depends on supply frequency. Supply frequency may change a bit here and there. If I have a frequency meter, I am lucky. I will note down right now what is the supply frequency. But this will be, see, frequency may change between say 48 Hertz to 51 Hertz like that. Supply frequency may change. But this, that error is not that much. What I am trying to tell, this difference is crucial. It is a small number. If instead of 2, if you make it 3, the difference will be quite large. Because this number is large, at 50 level something is changing. But nonetheless, that I can take care of by measuring the existing supply frequency with the help of a frequency meter. Therefore, the measurement of slip by a line frequency stroboscope is very accurate. If it is a 6-pole machine, you make 6 patterns. Flash it from line frequency. There are stroboscopes where manually the flashing rate can be changed. That way you don't connect, because induction motor runs with respect to some synchronous speed decided by supply frequency. So this is the best way. If it is a 6-pole machine, you mark with 6 patterns. Switch on the stroboscope at line frequency. See, in the anti-clockwise, if the rotor rotates physically in the clockwise direction, your pattern will appear to rotate in the anti-clockwise direction. And this I can, because it is a slow RPM, the slip speed, I can count how many patterns is moved. So from that I can make out what is the ns minus nr by this relationship and get the accurate value of slip of the induction motor. See, stroboscopic effect is very useful. Of course, it may cause sometimes problems. See, particularly fluorescent lamp itself is a cause of, in our day-to-day life, the stroboscopic effect is caused by fluorescent lamp also. Because here discharge jet takes place, from cathode to anode at a certain frequency. Unlike incandescent lamp, which gives you continuous light, that current passes through 0 in this one. So have you ever seen stroboscopic effect of fluorescent lamp? Yes, because you switch on your fan, you will find the blades can be distinctly seen. Number of blades appear to be more sometimes because of that stroboscopic action. And stroboscopic action, that's why in industries where several motors are there, which may be induction motor, this stroboscopic effect, which is naturally present there because of fluorescent lamp connected, the rotor may appear to rotate at a very slow RPM, although actually it is running at a very large RPM. Are you getting? Because of that stroboscopic effect, some patterns on the rotor marking will be there. Na? It will appear to remain stationary. And some people who is a bit careless, he may touch that rotor thinking it is running at a very low RPM. So that's why in high industries what they do, they will in a particular area they will connect the fluorescent lamps not from single source. See, some fluorescent lamp will be from R phase, some fluorescent lamp will be from Y phase and B phase, so that when this lamp is passing through zero current, others are not, like that. So stroboscopic effect which may cause accident can be avoided like that. But anyway, this is besides the point, you will learn about it. So this is about the slip measurement you should adopt. Now today I will start about the circle diagram of induction motor. So a good thing, I mean, nicely it is explained in Golding's book of measurement. You have Golding's book of measurement, electrical measurement, some stroboscopic method of that you can, of course, not relation with induction motor, basic idea of that is given. You go through that. Now today I will start the circle diagram of induction motor. Circle diagram of induction motor. Now what it is? See, in case of induction motor, as we have seen, and let us consider first the simplest diagram, equivalent circuit, that is neglecting stator impedance and no load impedance. You can very quickly predict the performance of the machine by resorting to this diagram. Of course, that will be not very accurate, but many things will come out of it. So this is the simplest equivalent circuit of an induction motor. Now obviously, if I ask you to calculate what is the torque developed by the induction motor at various slips, say S equal to 0.01, 1%, 2%, 5%, you calculate. So the same thing calculations you will be doing, I mean analyzing the same circuit with different values of S. Is not? What is the power factor? Power factor will also change like that. So every time same type of calculations you have to do, except that the value of slip has changed. See, operation of induction motor is reflected here. How? If loading is changed, slip will change and it will decide how much current the machine will draw, at what power factor, what is the output power, like that. So naturally, whether it is possible to have a graphical method for solving that instead of carrying on with same type of calculation, or for example say in the approximate but more accurate equivalent circuit of an induction motor, which looks like this one, R1 X1 is there, and here is X2 dashed, and here is R2 dashed by S. What is this current? This current is this V, per phase voltage, say V by this impedance, as I have told you, R2 dashed by S whole square plus X1 plus X2 dashed whole square, like this. So this is I2 dashed, under root this one. Now if you calculate I2 dashed, you know everything, because air gap power will be I2 dash square R2 dashed by S. From this you subtract copper loss. Everything depends on S now. Now, if I ask you calculate efficiency, torque developed by the induction motor at S equal to 0.04 and also at S equal to 0.05. See, you have to repeat the same calculations, identical calculations with two different values of slips. So, whether it is possible to express this problem rather graphically, so that for various values of slip I can easily read from some sort of technique. So that is the introductory part of circuit diagram. So I will first begin with this diagram, a simple equivalent circuit. Now as you know that to understand this one, the locus diagram, current locus diagram, current focus diagram in a series RL circuit. Of course, this is the basic of induction motor, but as an electrical engineer, this is also important to know what happens in a circuit. So that I will first discuss. That is, the problem is like this. Suppose you have got a inductive circuit whose reactance is X and resistance is R, and R is varied. This voltage is held fixed. This is fixed voltage, fixed, constant voltage. X is suppose fixed, and only thing this R is varied. The question is the tip of the current phasor, where it will lie. It can be shown it will lie on a circle. Now this is very simple to show. I will draw it like this. Suppose this is your supply voltage. This I will do in no time. Suppose this is your supply voltage. Say V, let us write V bar. For any arbitrary value of R, the current drawn by the circuit is suppose I bar, and it will be lagging in nature for some value of R. Okay. So suppose this is your I phasor for some value of R, and this is the power factor angle theta. Current will be lagging. Now the drops in X and R should add up to supply voltage. Okay. So one way of drawing is this way we generally draw. This is IR plus IX. Is not that I am not drawing. This is IR plus IX. If you do, you will get supply voltage. So this I will add. First I will add IX this side. So IX will be this one, 90 degree leading. That is, this is J I bar X, and then IR, which will be parallel to this one, I bar R. Okay, this way I just draw, and this is definitely 90 degree. This is 90 degree. Now what you do, the important step is this one. So this, you see, it is a triangle, phasor triangle. You divide all the sides, all the three sides of the triangle by this phasor, Jx bar. You know, if you multiply a phasor with some, Jx, I should write. Suppose you multiply, a phasor is there. You multiply with J, what happens? It moves 90 degree this way. If you divide by J, it will move 90 degree anticlockwise like this. Okay. So suppose what I do, I divide all the sides of this triangle, this, I divide by JJX. I do. Tell me where this side will go. Jx bar side, this side, divided by Jx. So Jx. So this becomes I bar, which is already drawn. So this phasor will transform to this one. This will be the tip of that. V bar by Jx you do. Where it will be? It will move by 90 degree. It will lie here like this. So this phasor then will become V bar. The length of this phasor will be V by X. V by X. And it is rotated by 90 degree like this. And this I bar R divided by Jx has to be this one. Because these two triangles, same magnitude I have divided, it has to be this one. Anyway, this is not of so much importance. But what is important is the relative angle between the two consecutive sides also will remain same. It will not change because of. So this angle too will remain 90 degree. Straight. No problem. So this was the current phasor. This is there. This is, and this length is V by X. Now suppose I vary R. It was there, I have changed the value of R. Do you think this length will change? No, V by X, it remains here. And the tip of the current phasor, wherever it will lie, that point and this point will make 90 degree. Therefore, this tip of this current phasor will lie on a circle whose diameter is V by X. That is, the tip of the current phasor will be here for any value of R. See, some for other value of R, it will be here, such that this angle is 90 degree. So it is this one, 90 degree, that makes it to lie on a circle, semicircle, on the diameter, angle is 90 degree. Therefore, it will lie on a circle like this. Therefore, the tip of the current phasor, in this case, if R is varied, will lie on this circle. And there is easy rule to do that. Of course, this is just for understanding sake. Suppose this is the supply voltage. You do it like this. This supply voltage. R is varied and varied from say 0 to infinity. That is the range of variation of R. Suppose R equal to 0. How much current it will draw? V by X, if suppose R equal to 0. And that current will be lagging the supply voltage by 90 degrees. So V by X will lie here. And for intermediate values, it will be somewhere here, like this. So this circle will look like this. This I can immediately make out. That is what I want to say. This is correct. But if somebody draws like this, it will be wrong, because this also represents lagging current. But it will, so this point corresponds to R equal to 0. What this point will correspond to? R equal to infinity. No current will be drawn. Impedance is infinitely large. Are you getting? So this is the easiest way of drawing. Now similarly, I'll just to complete this one, I will do like this. Suppose you have got a X here. You tell me, this is R. This is R. Suppose in this circuit X is varied. What will be the tip of the current locus? What you do? You do it like this. That is, the problem is, this is X, this is R. Suppose in a circuit, I am varying X, and this is supply voltage V. So this is supply voltage, you draw V, and this is suppose R. So what you do, the diameter of the circle is decided by the parameter which is not varying. So suppose X equal to 0. What will be the current drawn by the circuit? V by R, and it will be in phase with this one. So suppose this length is V by R, V by R. Then with this as diameter, you draw the circle. This is the tip of the current, locus of the tip of the current phasor. Locus of the tip of the current phasor. It will look like this. One can try with R's XC circuit, C is varied, how the current, with this common explanation of drawing phasor diagram, and that angle is 90 degree, like this. Anyway, that will not go too far. Only this much will help us. So in a induction motor, this I can therefore apply with advantage in this way. Suppose you consider now an induction motor where this is X2 dash leakage reactance and this is R2 dashed by S, which is varying with variation of slip. This is suppose supply voltage, and this is the current drawn at any time. This voltage is suppose held fixed at rated value, rated voltage per phase. See, this circle diagram is valid when voltage is constant. Supply voltage is constant. So rated voltage fixed. This I am not changing. How I am changing slip? Load will be changing on the shaft of the machine. This will change the value of slip of the machine. Now, how the circle diagram can be drawn? Quite easily. Suppose this is supply voltage, V bar per phase, phase rated voltage. Let us call it V1 bar per phase or V phase. Let me write. This is the current rod. What will be the diameter of the circle? B by this length will be V by V phase by x2 dashed. This will be the diameter of the circle. So then you find out what is its midpoint and then draw the circle. This will be the locus of the tip of the current phasor. Okay. Suppose machine is stationary, standstill condition. You have given full voltage, supply voltage. Then where the operating point will lie? Suppose S equal to 1, slip is 1. Then the impedance of the circuit or the angle by which this current will lag, that is this one, this point. Let us call this is capital S, standstill condition, S equal to 1. Such that this angle, which I will call theta 2s, tan theta 2s. S means capital S standstill condition. This will be simply x2 dashed by r2 dashed. This angle, theta 2s. Or rather, this angle is also same, theta 2s. So, this is the operating point at standstill condition. Slip of an induction motor will vary from what to what range? 0 to 1. So, this is suppose S equal to 1. Where is the point S equal to 0? This point. Because absolute no load condition, it will not draw any current. So, see, in this case, therefore, not the complete circle represents the operating point of the circle diagram. The variation of resistance will be valid variation, and it will be only up to this. At this part, the circuit will never go as a motor. Is that clear? Because here resistance cannot be varied from 0 to infinity. It is after all an equivalent circuit, where slip can change from 0 to 1. So, a part of this circle will be the locus of the current locus of the induction motor drawn. Achha. Anyway, now let us investigate what is happening at this point, standstill condition. See, let us drop a perpendicular from S to this diameter and call SM. Okay, SM is this one. This length OS is the current drawn. So, I will write here. Put it like this. So, I will write it like this. See, the input power to the machine per phase I am doing, per phase to the machine is how much? Voltage, phase voltage, into current, that is this length OS, into power factor angle, that is theta 2s, cosine theta 2 capital S. But OS cosine theta 2s is nothing but this length. So, this is V phase into this length SM length, the input power to the machine at S equal to 1, standstill condition. Therefore, what we find that from this operating point at standstill condition, if you drop a perpendicular, this length represents the power drawn from the supply, because V phase is constant. So, some other scale SM length SM Sm represents power. Some other scale, it is current scale you have drawn this one, but Sm can also very well represent power because V phase is constant. V phase is constant. Okay. So input power is Sm. This input power goes to where? At standstill condition. In the equivalent circuit of the induction motor X2 dashed. No, in this equivalent circuit where core loss everything is neglected, you look at the circuit and tell R2 dashed by 1. So all power is your air gap power first of all. This also represents air gap power. And S equal to 1. So all power is wasted in the rotor copper loss. That is the power wasted in this resistance. That is R2 dashed only. Okay, therefore, this Sm also represents Sm in this particular case at S equal to 1. Sm is your air gap power, power drawn is equal to your air gap power, because here in this equivalent circuit I have neglected stator copper loss, core loss, so this will be your air gap power. All power drawn from the supply will cross air gap and enter into rotor. So this is also air gap power. And at S equal to 1, this is also rotor copper loss. Rotor copper loss. This whole length. How much torque it develops? Starting, what you will do? Air gap power by 2 pi ns. So this Sm length also here in this particular case represents the torque developed, because that divided by synchronous speed gives you torque. So in some another scale it will give you the torque developed by the machine also. Clear? And what is the output power? Output power is 0, because machine has not started rotating, switched on the supply. It has developed torque. Now it will start rotating. Output mechanical power does not arise because there is no Nr, although torque is there. Torque into 2 pi Nr is output power. So this is the situation at S equal to 1. Now in this light I will now go to what is happening at a general operating point. Suppose motor is loaded such that it runs at slip S. Then how it will look like? So this was your V. This is suppose the circle, tip of the current locus. This is your V by X, X2 dashed. If I am wrong, correct me. And this is suppose the standstill operating point, capital S. That is, this point corresponds to S equal to 1. And this I called S. Now, when machine runs at a slip, say 5%, where do you think the operating point will lie? This side or this side? Left side. And in fact, it will somewhere, suppose, lie here. And it is a straight line. Suppose a general operating point at S. And as you can see, the power factor has changed now. Machine will operate at this power factor angle. Earlier it was theta 2s, capital S. This was theta 2s. This is the operating point. Now from the point P, you drop a perpendicular on the diameter, call it N. And this point you call anything, say Q. Obviously, this angle will be theta 2s. theta 2s, theta 2s, and this will be theta 2. Sorry, this is your sorry B phase. Now, at this general operating point, how much is the power input? Power input in this case, power input is V1, the current is OP, into cosine theta 2. OP cosine theta 2 is how much? Pn. So, V1 into Pn. So, in some other length, this Pn length will represent that in some other scale, whatever it is, because V1 is constant, Pn is the input power. Okay, just you, so Pn is the input power. Now, out of this input power can now be broken into two parts, Qn and Pq. So, you try to find out whether there exists a relationship between these two by considering this triangle and this triangle, some slip ratio, whether you can find out. Tomorrow I will continue with this.